here we have the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. And so a lot of times when things are discovered, just like the Fibonacci sequence was discovered, they start trying to see, where is this applied? Is it, and they start to see things appear in nature, and they start to make connections there. And then they also start to, try to look at things symbolically, and then just kind of fiddle around with the sequence, fiddle around with the numbers, and see if there's things that happen. And so that's what we're going to do. We're just going to kind of play with these numbers a little bit. So what we're going to do is we're going to take the nth Fibonacci number, and we're going to divide it by the Fibonacci number, the term before the nth Fibonacci number. So that's what that little -1, that represents the term before. So we're just going to take one term and divide it by the term before. That's basically what that means. So let's just start with the second Fibonacci number. The second Fibonacci number, this is the first, this is the second. The second Fibonacci number is 1, and we're going to divide it by the term that's before it, which is the first Fibonacci number. So we're just going to go 1 divided by 1, and 1 divided by 1 is just simply 1. And then what we're going to do is we're going to just try to take the third Fibonacci number and divide it by the term before it, which would be the second Fibonacci number. The third Fibonacci is 1, 2, 3. It's 2 divided by 1. 2 divided by 1 is 2. And we're just going to kind of continue this pattern and see if anything emerges. So now we're going to take the fourth Fibonacci number and divide it by the one before it, which would be the third Fibonacci number. So 3 divided by 2, which is 1.5. And we're just going to follow the pattern. The fifth Fibonacci number divided by the fourth Fibonacci number, which would be 5 divided by 3, which ends up being 1.66666. Repeating, so we put a little vinculum up there. That means that that number keeps repeating. The 6 keeps repeating on forever. And then we go to the sixth Fibonacci number, divide it by the one before it, which would be the fifth. So 8 divided by 5. And 8 divided by 5 is just, is 1.6 even. Then we're going to take the seventh Fibonacci number and divide it by the sixth Fibonacci number, 13 divided by 8, which is 1.625. And then the eighth Fibonacci divided by the seventh, 21 divided by 13, which is 1.615384. And then the ninth Fibonacci number divided by the eighth Fibonacci number, 34 divided by 21, which is 1.619047. And then the 10th Fibonacci number divided by the 9th Fibonacci number, 55 divided by 34, which is 1.617647. And then the 11th Fibonacci number divided by the 10th Fibonacci number, 89 divided by 55, which is 1.61818181818. So that 1 and the 8 are repeating. So I'm going to put the vinculum over the 1 and the 8, denoting that those two digits keep repeating on for forever. And then we're going to take the 12th Fibonacci number and divide it by the 11th Fibonacci number, 144 divided by 89, which would be 1.617978. The 13th Fibonacci number divided by the 12th, 233 divided by 144, which ends up being 1.61805555. That keeps repeating. The 14th Fibonacci number divided by the 13th, 377 divided by 233, which would be 1.618026. And then the 15th Fibonacci number divided by the 14th, 610 divided by 377, which would be 1.618037. And then the 16th Fibonacci number divided by the 15th Fibonacci number, 987 divided by 610. That would be 1.618038. And then lastly, the 17th Fibonacci number divided by the 16th, 1,597 divided by 987, which would be 1.618034. And we could just keep repeating this process, indefinitely. But what mathematicians would be looking for is to see if there's a pattern that emerges. Does something happen? When we keep following this nth divided by the term before it, what happens with these numbers? So what I'm going to do is I'm going to go ahead and I'm just going to plot these numbers. I got this little vertical number line over here. And so the first answer we got was just a 1. So I'm going to just put a little point here on 1. Then what we got next was a 2, Well, not a whole lot going on. But the next answer we got was 1.5. Okay, in the middle. And then the next answer we got was 1.66666. So that's, between 1.6 and 1.7, closer to 1.7, right about there. I'm just approximating. The next answer we got was just 1.6 even. Okay. And then we got 1.625, which is about halfway between those two. And then 1.61538, which would be right about there. And then 1.619, right about there. And then 1.617, right about there. And then 1.618181818. And then 1.617. And then 1.618. 05, 1.61802, 1.6803, 1.6032, 1.61804. So, what's happening is at the beginning we were kind of bouncing back and forth, but what's happening is this pattern, taking the nth and dividing it by the term before it. We are approaching a particular number. The more, if we carry out this this pattern more and more, what we're going to do is we're going to get closer and closer to a particular number. You're going to do some fractal problems later in chapter 12. And what they call this is being attracted to something. The numbers are drawn towards a particular number. And what this number is that they're drawn to, it actually has a name. It's called the golden ratio. Ratio. Whoops. And it's denoted by phi. And it's approximately, and I say approximately, 1.618 It's approximately that. But what I'm going to say phi is equal to is the algebraic notation of 1 plus the square root of 5 over 2. Now that's exactly what this number is going to be. So the golden ratio it's 1.618, but it also has another way of denoting itself is if we do the same numbers, but we have 1 minus the square root of 5 over 2, we can say that it's approximately equal to negative 0.618. So this is the golden ratio, and the golden ratio shows up in a lot of different places within nature and modern technology and things like that. And from the golden ratio, what we can do is we can derive something called the golden rectangle. Now the golden rectangle takes into the golden ratio, which the golden ratio is derived from looking at and messing with the ratio of the Fibonacci numbers. So Fibonacci numbers to golden ratio to golden rectangle. And if we're looking at the golden rectangle, what the golden rectangle is phi. The width is phi, which is, approximately 1.618. And then the length of this is 5 plus 1, which would be 1.618 plus 1, which would be approximately 2.618. Those would be the dimensions. This is the phi. See, phi is this much. That's that. This right here, that's the plus 1. So phi plus 1. That's how we denote this. Now, these particular dimensions of 1.618 by 2.618, this particular rectangle for some reason is very, very visually pleasing to our eyes. And you can take this rectangle, you can, turn it the other way. Imagine putting it on a copy machine and shrinking it down or enlarging it. And this rectangle shows up in a lot of different areas. And you guys some of you are going to be actually doing your learning team presentations on this particular concept. So you guys will be showing some of the other representations of where this is shown. But from the golden rectangle, we can also arrange the golden rectangles into a golden spiral, and you'll be seeing that in another link coming up. But all of this stuff is connected. So I will really look forward to watching your presentations.